What if the universe had a secret chapter, a time so dark and mysterious that even light itself seemed to vanish? This isn't science fiction, it's a real era in cosmic history known as the Dark Ages. For hundreds of millions of years, the universe was cloaked in shadow, a silent stage where the first seeds of everything we know today were quietly planted. But what exactly happened during this enigmatic period, and how did the universe transform from a vast, empty void into the vibrant cosmos we see today? In this video, we're diving deep into 30 fascinating theories that attempt to unravel the mysteries of the universe's dark ages, from the role of dark matter and the birth of the first stars to the influence of cosmic radiation and the formation of the earliest galaxies. Each theory offers a unique glimpse into this hidden chapter of our cosmic story. By the end of this journey, you'll not only understand why this era is so crucial to our existence, but also discover how scientists are piecing together clues from the ancient universe to uncover its secrets. So, are you ready to step into the shadows and explore the mysteries of the Dark Ages? Stay with us, because what you're about to learn might just change the way you see the universe forever. Now, let's turn our attention to the first theory, which takes us back to the very beginning: the cosmic microwave background, or CMB. This faint glow, often called the afterglow of the Big Bang, is one of the most important pieces of evidence we have about the early universe. But how does it connect to the Dark Ages? The CMB is essentially a snapshot of the universe when it was just 380,000 years old. At this point, the universe had cooled enough for protons and electrons to combine and form neutral hydrogen atoms. This event, known as recombination, allowed light to travel freely for the first time, creating the CMB we detect today. But here's where it gets fascinating: this light carries imprints of the universe's conditions at that time, including the seeds of the Dark Ages. During the Dark Ages, the universe was filled with neutral hydrogen, which absorbed light, making it invisible to us. The CMB, however, gives us a glimpse of the universe just before this era began. By studying tiny fluctuations in the CMB, scientists can map the distribution of matter in the early universe. These fluctuations are like cosmic fingerprints, revealing how matter clumped together and eventually led to the formation of the first stars and galaxies. In essence, the CMB is a time capsule, preserving the universe's state at the edge of the Dark Ages. It tells us not only how the universe looked before this mysterious era, but also provides clues about what triggered the end of the Dark Ages, the birth of the first stars. So, while the Dark Ages themselves remain shrouded in mystery, the CMB offers a powerful tool to peer into this hidden chapter of cosmic history. And as we'll see in the next theory, the role of dark matter adds another layer of intrigue to this story. Now, let's shift our focus to something even more mysterious: dark matter. While the cosmic microwave background gives us a snapshot of the early universe, dark matter plays a crucial role in shaping the cosmic structures we see today. But what exactly is dark matter, and how did it influence the universe during the Dark Ages? Dark matter is an invisible substance that doesn't emit, absorb, or reflect light, making it impossible to detect with traditional telescopes. Yet, its presence is undeniable. Scientists estimate that dark matter makes up about 85% of all matter in the universe. During the Dark Ages, this mysterious substance acted as the cosmic scaffolding, providing the gravitational pull needed for matter to clump together. Imagine the early universe as a vast, empty canvas. Dark matter was the first brushstroke, creating slight ripples in the fabric of space. These ripples, though tiny, were enough to attract ordinary matter, like hydrogen gas, toward them. Over time, these clumps of matter grew denser, eventually forming the seeds of the first stars and galaxies. Without dark matter, the universe might have remained a featureless expanse with no structures to light up the cosmic darkness. But here's where it gets even more intriguing. Dark matter didn't just help structures form, it also influenced how they evolved. The gravitational pull of dark matter dictated where galaxies would form and how they would cluster together. This invisible framework laid the groundwork for the cosmic web we see today, a sprawling network of galaxies and voids that stretches across the universe. So, while dark matter remains one of the greatest mysteries in science, its impact on the Dark Ages is undeniable. It was the unseen architect quietly shaping the universe during its darkest chapter. And as we'll see in the next theory, the birth of the first stars would eventually bring an end to this era, illuminating the cosmos in a spectacular way. Now, let's turn our attention to the cosmic dawn, the moment when the first stars ignited and brought light to the universe. These stars, known as population 3 stars, were unlike anything we see today. They were massive, hot, and incredibly bright, made almost entirely of hydrogen and helium, the simplest elements forged in the Big Bang. Their birth marked the end of the Dark Ages and the beginning of a new era, one where the universe would no longer be shrouded in darkness. Population 3 stars were the pioneers of the cosmos. As they formed within the dense clouds of gas pulled together by dark matter, they began to burn through nuclear fusion, releasing intense ultraviolet light. This light didn't just illuminate their surroundings, it fundamentally changed the universe. The ultraviolet radiation from these stars was so powerful that it began to strip electrons from the neutral hydrogen atoms that filled the cosmos, a process known as reionization. Reionization was a turning point. For hundreds of millions of years, the universe had been filled with neutral hydrogen, which absorbed light and kept the cosmos dark. But as population 3 stars lit up, their radiation began to ionize this hydrogen, turning it into a plasma of free electrons and protons. This allowed light to travel freely through space for the first time, effectively ending the Dark Ages and ushering in the epoch of reionization. But the impact of these first stars didn't stop there. Their intense radiation also heated the surrounding gas, preventing it from collapsing into new stars too quickly. This created a feedback loop regulating the formation of future stars and galaxies. And when these massive stars eventually died, they exploded as supernovae, scattering heavier elements like carbon and oxygen into the cosmos. These elements would later become the building blocks for planets, life, and everything we see around us today. So, while the Dark Ages were a time of cosmic silence, the birth of population 3 stars was the universe's first symphony. They not only brought light to the darkness, but also set the stage for the rich, complex universe we inhabit today. And as we'll explore next, the formation of the first galaxies would take this cosmic evolution to an entirely new level. Now, shifting our gaze to another fascinating possibility, let's explore the mystery of primordial black holes. These enigmatic objects, if they existed during the Dark Ages, could have played a significant role in shaping the early universe. Unlike the black holes we know today, which form from the collapse of massive stars, primordial black holes are thought to have emerged in the chaotic moments following the Big Bang. Tiny yet incredibly dense, these black holes could have been scattered throughout the cosmos, silently influencing the universe's evolution. One of the most intriguing aspects of primordial black holes is their potential to explain some of the universe's greatest mysteries. For instance, they could account for a portion of the dark matter that makes up much of the cosmos. While dark matter itself remains invisible, its gravitational effects are undeniable. Primordial black holes, if they exist in large numbers, might contribute to this unseen mass, helping to explain how galaxies and cosmic structures formed so quickly after the Big Bang. But how would these black holes have impacted the Dark Ages? During this period, the universe was filled with neutral hydrogen, and light was unable to travel freely. Primordial black holes, if present, could have acted as gravitational anchors, pulling matter toward them and creating dense regions of gas. These regions might have served as the seeds for the first stars and galaxies, accelerating the end of the Dark Ages. Additionally, as these black holes absorbed matter, they could have emitted radiation, subtly heating the surrounding gas and influencing the process of reionization. The idea of primordial black holes also raises questions about their ultimate fate. Some theories suggest they could have evaporated over time due to a process called Hawking radiation, while others propose that they might still exist today, lurking in the shadows of the cosmos. If detected, these ancient black holes could provide invaluable insights into the conditions of the early universe and the forces that shaped it. As we ponder the role of primordial black holes, we're reminded of how much remains unknown about the Dark Ages. These mysterious objects, if they existed, could have been silent architects of the universe's transformation, guiding it from darkness to light. And as we'll see next, the influence of dark energy during this period adds yet another layer of complexity to this cosmic puzzle. Now, let's turn our attention to another cosmic force that may have quietly shaped the universe during its dark ages: dark energy. While dark energy is often associated with the accelerated expansion of the universe in more recent times, its influence might have been at work even in those early, shadowy epochs. This mysterious form of energy, which makes up about 68% of the universe, is thought to permeate all of space, exerting a repulsive force that counteracts gravity. But how could it have played a role during the Dark Ages, when the universe was still in its infancy? During the Dark Ages, the universe was expanding, but at a much slower rate compared to the rapid inflation that occurred immediately after the Big Bang. Dark energy, if it was present, might have subtly influenced this expansion, gradually pushing galaxies and cosmic structures apart. While its effects would have been far less dramatic than in the modern universe, even a small influence could have had profound implications. For instance, dark energy's repulsive force might have helped create the vast cosmic voids we observe today, regions of space that are almost entirely empty, stretching across billions of light years. But here's where things get even more intriguing. Some theories suggest that dark energy's influence could have interacted with other cosmic processes during the Dark Ages. For example, as the first stars and galaxies began to form, dark energy's push against gravity might have affected how matter clumped together. This delicate balance between expansion and gravitational collapse could have shaped the distribution of galaxies, influencing the large-scale structure of the universe we see today. Another fascinating possibility is that dark energy's presence might have subtly altered the rate at which the universe cooled during the Dark Ages. As the cosmos expanded, the temperature of the cosmic microwave background radiation dropped, and dark energy's influence could have played a role in this cooling process. This, in turn, might have affected the formation of the first stars and galaxies, potentially delaying or accelerating the end of the Dark Ages. Of course, much about dark energy remains a mystery. We don't yet fully understand its nature or how it behaves over cosmic timescales. But if it was indeed active during the Dark Ages, it could have been a silent yet powerful force, quietly shaping the universe's evolution in ways we're only beginning to uncover. As we continue to explore this enigmatic energy, we may find that its fingerprints are etched into the very fabric of the cosmos, even in those ancient dark times. And speaking of cosmic forces, our next theory takes us into the realm of neutral hydrogen, the dominant element that filled the universe during the Dark Ages and played a crucial role in keeping it shrouded in darkness. Now, let's shift our focus to one of the most defining features of the Dark Ages: neutral hydrogen. This simple yet pervasive element played a starring role in keeping the universe cloaked in darkness for hundreds of millions of years. After the initial glow of the Big Bang faded, the cosmos was filled with a sea of neutral hydrogen atoms, hydrogen that hadn't yet been ionized, meaning its single electron remained bound to its nucleus. This neutral hydrogen acted like a cosmic fog, absorbing the light that tried to pass through it and preventing stars and galaxies from illuminating the universe. During this time, the universe was a vast, cold expanse with temperatures dropping as it expanded. Neutral hydrogen thrived in these conditions, forming a thick, opaque barrier that blocked ultraviolet light from traveling freely. This is why the Dark Ages earned their name, not because there was no light, but because the light that did exist couldn't travel far before being absorbed by these hydrogen atoms. Imagine trying to see through a dense, endless mist. That's what the universe was like during this era. But neutral hydrogen didn't just block light. It also played a crucial role in setting the stage for the universe's eventual transformation. As the first stars and galaxies began to form, their intense ultraviolet radiation started to ionize the surrounding hydrogen, stripping electrons from their nuclei. This process, known as reionization, gradually cleared the cosmic fog, allowing light to travel freely once again. It marked the end of the Dark Ages and the dawn of a new, luminous era in the universe's history. Interestingly, the way neutral hydrogen absorbed light during the Dark Ages has left behind a unique signature that scientists can still detect today. This signature, known as the 21-centimeter line, is a faint radio signal emitted by neutral hydrogen. By studying this signal, astronomers can peer back in time and map the distribution of hydrogen during the Dark Ages, offering us a glimpse into the universe's shadowy past. So, while neutral hydrogen may have kept the universe dark for a time, it also held the key to its eventual illumination. Its presence not only defined the Dark Ages, but also paved the way for the cosmic structures and light-filled galaxies we see today. And as we continue to explore this pivotal element, we uncover more about how the universe transitioned from darkness to light. Next, we'll dive into how the first galaxies began to form toward the end of the Dark Ages, bringing an end to this mysterious chapter in cosmic history. As we move forward in our exploration of the Dark Ages, we arrive at a pivotal moment in cosmic history, the formation of the first galaxies. This marked the beginning of the end for the universe's long period of darkness. Picture this: after hundreds of millions of years shrouded in a dense fog of neutral hydrogen, the cosmos was finally ready to take its first steps toward becoming the vibrant, light-filled expanse we know today. The seeds for these first galaxies were planted by tiny fluctuations in the density of matter left over from the Big Bang. These fluctuations, though minuscule at first, grew over time as gravity pulled matter together. Denser regions began to collapse under their own weight, forming clumps of gas that would eventually ignite into the first stars. But these stars didn't form in isolation. They clustered together, bound by gravity, to create the earliest galaxies. These primordial galaxies were unlike anything we see today. They were smaller, simpler, and composed almost entirely of hydrogen and helium, the only elements present in significant quantities at the time. Yet, despite their simplicity, they were incredibly powerful. The stars within these galaxies burned hot and bright, emitting intense ultraviolet radiation that began to ionize the surrounding hydrogen gas. This process, known as reionization, was like turning on a cosmic light switch, gradually clearing the fog of neutral hydrogen that had dominated the Dark Ages. As more stars and galaxies formed, the universe began to transform. The once opaque expanse started to glow with the light of countless stars, and the first galaxies grew larger and more complex. Over time, they merged with one another, forming the larger, more intricate structures we see in the modern universe. This era of galaxy formation didn't just end the Dark Ages. It laid the foundation for the cosmic web of galaxies, clusters, and superclusters that define the universe today. What's truly remarkable is that we can still observe the remnants of these early galaxies. Using powerful telescopes, astronomers have detected faint, distant galaxies that formed just a few 100 million years after the Big Bang. These ancient objects provide a window into the universe's formative years, helping us piece together the story of how the first galaxies emerged and how they shaped the cosmos. The formation of the first galaxies was a turning point in the universe's history, a moment when darkness gave way to light. It's a reminder that even in the vast, cold expanse of space, change is constant, and the seeds of transformation are always present. Next, we'll explore how the rapid expansion of the universe during inflation set the stage for the Dark Ages, connecting the dots between the universe's earliest moments and its shadowy adolescence. Now, let's rewind the cosmic clock even further, back to a time when the universe was just a fraction of a second old. This brings us to the era of cosmic inflation, a period of unimaginably rapid expansion that set the stage for everything that followed, including the Dark Ages. Imagine the universe as a tiny, dense seed smaller than an atom, suddenly stretching out in all directions faster than the speed of light. In less than a blink of an eye, it grew exponentially, smoothing out irregularities and laying the groundwork for the cosmos we see today. This rapid expansion wasn't just a random event, it was a crucial step in shaping the universe's destiny. During inflation, quantum fluctuations, those tiny ripples in the fabric of space-time, were stretched to cosmic scales. These fluctuations became the seeds for all the structures we see in the universe today, from galaxies to galaxy clusters. Without inflation, the universe might have remained a chaotic, uneven mess, and the Dark Ages might never have happened. But how does this connect to the Dark Ages? Well, inflation didn't just create the conditions for structure formation, it also determined the density and distribution of matter in the early universe. As the universe expanded and cooled, these density variations began to grow, eventually leading to the clumping of matter that formed the first stars and galaxies. However, before those stars could ignite, the universe had to pass through its dark phase, a time when neutral hydrogen dominated and light couldn't travel freely. Inflation also played a role in setting the stage for the cosmic microwave background, the faint afterglow of the Big Bang that we discussed earlier. This radiation, which fills the universe, is a snapshot of the universe just 380,000 years after the Big Bang. It shows us the density variations that inflation created, the very same variations that would later grow into galaxies and end the Dark Ages. So, while cosmic inflation might seem like a distant and abstract concept, its effects are woven into the very fabric of the universe. It's the reason we have galaxies, stars, and ultimately the light that ended the Dark Ages. Next, we'll dive into the role of quantum fluctuations, exploring how these tiny ripples in the early universe grew into the cosmic structures we see today. Now, shifting our focus to the microscopic, let's zoom in on the role of quantum fluctuations during the universe's earliest moments. These tiny, unpredictable ripples in the fabric of space-time might seem insignificant, but they played a monumental role in shaping the cosmos as we know it. Picture the early universe as a bubbling, chaotic soup of energy, where quantum fluctuations caused minuscule variations in density. These fluctuations, though incredibly small, were stretched to enormous scales during cosmic inflation, becoming the seeds for all the structures we observe today. As the universe expanded and cooled, these density variations began to grow, acting like cosmic blueprints for the formation of galaxies, stars, and even galaxy clusters. Without these tiny ripples, the universe might have remained a smooth, featureless expanse, devoid of the rich tapestry of structures we see today. It's fascinating to think that the galaxies we observe, with their swirling arms and glowing cores, owe their existence to these microscopic quantum events. But how did these fluctuations influence the Dark Ages? During this period, neutral hydrogen dominated the universe, absorbing light and keeping it shrouded in darkness. The density variations left behind by quantum fluctuations determined where matter would eventually clump together. These clumps, over hundreds of millions of years, grew into the first stars and galaxies, whose light would eventually pierce through the darkness and end the Dark Ages. In a way, quantum fluctuations were the architects of the universe's first light. What's even more remarkable is that we can still see the imprint of these fluctuations today in the cosmic microwave background. This faint glow, a relic of the early universe, shows us the density variations that quantum fluctuations created. It's like a cosmic fingerprint, revealing the origins of the structures that would later illuminate the universe. So, while quantum fluctuations might seem like a concept confined to the realm of particle physics, their impact is written across the cosmos. They are the hidden hand that guided the formation of the universe from its earliest moments to the end of the Dark Ages. Next, we'll explore another piece of the cosmic puzzle, the mystery of the missing baryon problem and its implications for understanding this enigmatic era. Now, let's turn our attention to one of the most puzzling mysteries in cosmology, the missing baryon problem. Baryonic matter, the ordinary stuff that makes up stars, planets, and even us, seems to be playing a cosmic game of hide and seek. Scientists have long known that the amount of baryonic matter predicted by the Big Bang theory doesn't quite match what we observe in the universe today. So, where did all this missing matter go, and what does it mean for the Dark Ages? During the Dark Ages, the universe was filled with neutral hydrogen, a key component of baryonic matter. But as the cosmos evolved, much of this matter seemed to vanish from our observations. The mystery lies in the fact that while we can account for some of it in stars, galaxies, and gas clouds, a significant portion remains unaccounted for. This missing baryonic matter is thought to exist in a form that's incredibly difficult to detect. Hot, diffuse gas spread throughout the vast cosmic web. This cosmic web, a network of filaments connecting galaxies, is believed to hold the missing baryons in the form of warm hot intergalactic medium, or WIM. This gas is so hot and thinly spread that it doesn't emit much light, making it nearly invisible to traditional telescopes. However, advanced instruments and techniques, such as X-ray observations and the study of absorption lines in the light from distant quasars, have started to reveal hints of its presence. These findings suggest that the missing baryons might be hiding in plain sight, woven into the fabric of the universe itself. But why does this matter for the Dark Ages? The distribution and behavior of baryonic matter played a crucial role in shaping the universe during this era. The density and movement of this matter influenced how and where the first stars and galaxies formed. If a significant portion of baryonic matter was spread out in this elusive WIM, it could have affected the timeline and process of reionization, the event that brought the Dark Ages to an end. Understanding where this missing matter is and how it behaved could provide critical insights into the transition from darkness to light in the early universe. The missing baryon problem isn't just a cosmic curiosity, it's a key piece of the puzzle in understanding the universe's evolution. By solving this mystery, we could unlock new details about the Dark Ages and the forces that shape the cosmos as we know it. Next, we'll explore another fascinating aspect of this era, the role of primordial magnetic fields and how they might have influenced the universe during its darkest chapter. Now, let's shift our focus to another intriguing aspect of the Dark Ages, the role of primordial magnetic fields. These ancient magnetic fields, thought to have formed in the very early universe, could have played a subtle yet significant role in shaping the cosmos during this mysterious era. While we often think of gravity and radiation as the dominant forces in the early universe, magnetic fields might have quietly influenced the way matter clumped together, setting the stage for the formation of the first stars and galaxies. Primordial magnetic fields are believed to have originated from tiny fluctuations in the fabric of space-time during the universe's infancy. These fluctuations, amplified by the rapid expansion of the cosmos, could have generated weak but widespread magnetic fields. While these fields were likely much weaker than the ones we're familiar with today, like those around Earth or in stars, they might have had a profound impact on the behavior of charged particles, such as electrons and protons during the Dark Ages. One of the key ways these magnetic fields could have influenced the universe is by affecting the motion of ionized gas. Even though the universe was mostly filled with neutral hydrogen during the Dark Ages, there were still traces of ionized particles. Primordial magnetic fields could have guided the movement of these particles, subtly altering how matter distributed itself across the cosmos. This, in turn, might have influenced where and how the first structures began to form, potentially shaping the cosmic web we see today. Another fascinating possibility is that these magnetic fields could have played a role in the formation of the first stars. By influencing the way gas clouds collapsed and fragmented, magnetic fields might have determined the size and distribution of these early stellar nurseries. Some theories even suggest that magnetic fields could have helped regulate the flow of energy within these clouds, affecting how efficiently stars formed and how bright they shone. But detecting these ancient magnetic fields is no easy task. Unlike the cosmic microwave background, which provides a clear snapshot of the early universe, primordial magnetic fields leave behind much fainter traces. Scientists are exploring innovative methods to uncover their presence, such as studying the polarization of light from distant galaxies or looking for subtle distortions in the cosmic microwave background. These efforts could one day reveal whether magnetic fields were indeed a hidden force during the Dark Ages. Understanding the role of primordial magnetic fields could provide new insights into how the universe transitioned from darkness to light. By piecing together their influence, we might uncover another layer of the cosmic story, shedding light on the forces that shaped the early universe. Next, we'll explore how the Dark Ages came to an end, diving into the dramatic event known as the Epoch of reionization and what it means for our understanding of cosmic history. Now, let's turn our attention to one of the most pivotal moments in cosmic history, the end of the Dark Ages. This dramatic transition marked the universe's shift from a cold, dark expanse to a vibrant, illuminated cosmos, and it all began with an event known as the Epoch of reionization. But what exactly caused this cosmic transformation, and how did it unfold? The Dark Ages came to an end when the first stars and galaxies began to form, flooding the universe with light. These early stars, often referred to as population 3 stars, were unlike anything we see today. They were massive, hot, and incredibly bright, emitting intense ultraviolet radiation. This radiation had the power to strip electrons from neutral hydrogen atoms, a process known as ionization. As more and more hydrogen became ionized, the universe gradually transitioned from being opaque to transparent, allowing light to travel freely across vast distances. But the story doesn't end there. The formation of the first galaxies played a crucial role in this cosmic shift. As galaxies grew and merged, they created environments where stars could form in large numbers. These galaxies acted like cosmic lighthouses, their collective light contributing to the reionization of the universe. Over time, the combined radiation from countless stars and galaxies ionized nearly all the neutral hydrogen in the universe, bringing an end to the Dark Ages and ushering in the era of light we now inhabit. One of the key drivers of this transition was the feedback from these early stars and galaxies. As stars formed and died, they released energy and heavy elements into their surroundings, enriching the cosmos and paving the way for future generations of stars. Supernovae, the explosive deaths of massive stars, played a particularly important role. These cataclysmic events not only ionized surrounding gas, but also seeded the universe with the building blocks for planets, life, and everything we see today. Scientists have been able to piece together this cosmic story by studying distant quasars, some of the brightest objects in the universe. The light from these quasars passes through clouds of gas, leaving behind telltale signatures of neutral and ionized hydrogen. By analyzing these signatures, researchers can map out how and when reionization occurred, providing a clearer picture of this transformative era. The end of the Dark Ages was not an instantaneous event but a gradual process that unfolded over hundreds of millions of years. It was a time of cosmic rebirth as the universe transitioned from darkness to light, setting the stage for the rich and complex cosmos we observe today. Next, we'll explore another fascinating aspect of this era, the role of cosmic neutrinos and how these elusive particles might have influenced the Dark Ages. Now, let's shift our focus to one of the most elusive players in the cosmic drama of the Dark Ages, cosmic neutrinos. These tiny, nearly massless particles are often called the ghosts of the universe because they rarely interact with matter, making them incredibly difficult to detect. Yet, despite their elusive nature, neutrinos may have played a surprisingly significant role in shaping the universe during its darkest era. Neutrinos were born in the fiery aftermath of the Big Bang, flooding the cosmos in unimaginable numbers. As the universe expanded and cooled, these particles continued to zip through space, barely interacting with anything around them. But even though they rarely collide with other matter, their sheer abundance meant they could still influence the universe in subtle but profound ways. One of their key roles during the Dark Ages was in regulating the temperature of the cosmos. During this period, the universe was filled with neutral hydrogen gas, which absorbed light and kept the cosmos in darkness. However, neutrinos, with their unique ability to travel vast distances without being absorbed, could carry energy across the universe. This energy transfer may have helped to slightly warm regions of space, creating tiny fluctuations in temperature. These fluctuations, though small, could have had a ripple effect, influencing where and how the first stars and galaxies began to form. Another intriguing possibility is that neutrinos may have contributed to the formation of cosmic structures. While dark matter is often credited with providing the gravitational scaffolding for galaxies and clusters, neutrinos could have played a supporting role. Their high speeds and low masses meant they didn't clump together like dark matter, but their gravitational influence might have subtly shaped the distribution of matter in the early universe. This could have affected how quickly structures like galaxies and galaxy clusters emerged, potentially speeding up the end of the Dark Ages. Scientists are still working to understand the full impact of neutrinos during this mysterious era. One of the challenges is that neutrinos are so difficult to detect, especially those from the early universe. However, advancements in technology, such as more sensitive detectors and powerful telescopes, are bringing us closer to uncovering their secrets. By studying the faint traces neutrinos left behind, researchers hope to piece together how these ghostly particles influenced the universe's transition from darkness to light. As we continue to explore the role of cosmic neutrinos, one thing is clear: even the smallest and most elusive particles can have a profound impact on the grand story of the cosmos. Next, we'll dive into another fascinating theory: the speculative idea that cosmic strings might have played a role in shaping the Dark Ages. Now, let's turn our attention to a theory that stretches the boundaries of our imagination: the influence of cosmic strings during the Dark Ages. Cosmic strings are hypothetical, one-dimensional structures that some scientists believe could have formed in the early universe. These incredibly thin, yet unimaginably dense, filaments are thought to be remnants of the rapid expansion of space during the cosmic inflation period. While their existence remains unconfirmed, the idea that they might have played a role in the Dark Ages opens up a fascinating realm of possibilities. Imagine cosmic strings as cosmic scars left over from the universe's birth. These structures, if they exist, would carry immense amounts of energy and could have acted as gravitational lenses, warping the fabric of space-time around them. During the Dark Ages, when the universe was still a vast, dark expanse of neutral hydrogen, cosmic strings might have influenced the distribution of matter in subtle but significant ways. Their gravitational pull could have caused slight ripples in the density of matter, creating regions where gas clumped together more densely. Over time, these denser regions could have become the seeds for the first stars and galaxies, helping to bring light to the universe. Another intriguing aspect of cosmic strings is their potential to generate gravitational waves. If these strings vibrated or collided, they could have sent ripples through space-time, leaving behind faint imprints that might still be detectable today. These gravitational waves could have interacted with the neutral hydrogen gas, subtly altering its behavior and contributing to the complex processes that eventually ended the Dark Ages. While this idea is still speculative, it offers a tantalizing glimpse into how even the most exotic cosmic phenomena might have shaped the universe's evolution. Despite their speculative nature, cosmic strings represent an exciting area of research. Scientists are actively searching for evidence of their existence, using advanced tools like gravitational wave detectors and cosmic microwave background observations. If cosmic strings are ever confirmed, they could provide crucial insights into not only the Dark Ages but also the very origins of the universe itself. As we ponder the potential influence of cosmic strings, we're reminded that the universe is full of mysteries waiting to be unraveled. Next, we'll explore another captivating theory: the role of gravitational waves from the early universe and how they might hold clues about the Dark Ages. Now, shifting our focus to another fascinating aspect of the Dark Ages, let's explore the role of gravitational waves. These ripples in the fabric of space-time, first predicted by Albert Einstein over a century ago, are not just a modern scientific marvel. They might also hold the key to understanding the universe's mysterious early years. Gravitational waves are created by some of the most violent and energetic events in the cosmos, such as the collision of black holes or the explosive deaths of massive stars. But what if these waves could also tell us about the Dark Ages, a time when the universe was shrouded in darkness? During the Dark Ages, the universe was filled with neutral hydrogen gas, and light as we know it didn't yet exist. However, gravitational waves, unlike light, can travel through this dense, opaque medium without being absorbed or scattered. This means that if gravitational waves were generated during this era, they could carry information about the conditions of the early universe directly to us, acting as cosmic messengers from a time long before the first stars ignited. Scientists believe that these waves might have been produced by events like the merging of primordial black holes or the vibrations of cosmic strings, as we discussed earlier. One of the most exciting possibilities is that gravitational waves from the Dark Ages could still be detectable today. These ancient ripples would be incredibly faint, but advanced instruments like the Laser Interferometer Gravitational Wave Observatory, or LIGO, and future space-based detectors like the Laser Interferometer Space Antenna, or LISA, are designed to pick up even the tiniest signals. If we could detect these waves, they might reveal details about the distribution of matter, the formation of early structures, and even the nature of dark matter and dark energy during the Dark Ages. Moreover, gravitational waves could help us understand how the universe transitioned from a dark, featureless expanse to one filled with light and structure. For instance, if these waves interacted with the neutral hydrogen gas, they might have subtly influenced its behavior, contributing to the eventual collapse of gas clouds that led to the birth of the first stars and galaxies. This would provide a direct link between the Dark Ages and the epoch of reionization, when the universe began to light up. While the detection of gravitational waves from the Dark Ages remains a challenge, the potential rewards are immense. These waves could offer a unique window into a time that has so far been hidden from our view, helping us piece together the story of how the universe evolved from darkness to light. As we continue to refine our technology and deepen our understanding, the whispers of these ancient ripples might one day reveal the secrets of the Dark Ages. With this intriguing possibility in mind, let's move on to another captivating theory: the mystery of the first molecules and how they formed during this enigmatic period in cosmic history. Now, let's turn our attention to one of the most fundamental puzzles of the Dark Ages: the mystery of the first molecules. During this era, the universe was a vast, cold expanse filled with neutral hydrogen gas, but it wasn't entirely empty of complexity. In fact, this was the time when the very first molecules began to form, setting the stage for the cosmic chemistry that would eventually lead to the birth of stars and galaxies. Among these early molecules, molecular hydrogen played a crucial role, acting as a building block for the universe's first structures. Molecular hydrogen, or H2, is a simple molecule made up of two hydrogen atoms bonded together. While it might seem basic, its formation during the Dark Ages was anything but straightforward. In the early universe, temperatures were incredibly high and atoms were ionized, meaning electrons were stripped away from their nuclei. As the universe expanded and cooled, electrons began to recombine with protons, forming neutral hydrogen atoms. But for molecular hydrogen to form, these atoms needed to collide and bond in just the right way, a process that required specific conditions and a bit of cosmic luck. One of the key mechanisms for forming molecular hydrogen involved the help of free electrons. These electrons acted as catalysts, allowing hydrogen atoms to come together and form molecules. This process was slow and inefficient, but over millions of years, tiny amounts of molecular hydrogen began to accumulate in the universe. This might not sound like much, but even a small amount of molecular hydrogen had a profound impact. It acted as a coolant, allowing gas clouds to lose heat and collapse under their own gravity, eventually forming the first stars and galaxies. The formation of molecular hydrogen also had another important consequence. It marked the beginning of chemistry in the universe. Before this, the cosmos was dominated by simple atoms and ions, but with the emergence of molecules, the universe gained the ability to create more complex structures. This was the first step toward the rich chemical diversity we see today, from the water in our oceans to the organic molecules that make up life itself. Scientists have been working to understand exactly how and where these first molecules formed. One theory suggests that they may have originated in the densest regions of the early universe, where gas clouds were more likely to collide and bond. Another idea is that the first molecules formed on the surfaces of tiny dust grains, which acted as a kind of cosmic workshop for chemical reactions. While these theories are still being explored, one thing is clear: the formation of molecular hydrogen was a turning point in cosmic history, paving the way for the universe to evolve from a dark, featureless void into a vibrant, star-filled expanse. As we continue to unravel the mysteries of the Dark Ages, the story of the first molecules reminds us just how intricate and interconnected the universe truly is. From the simplest bonds between hydrogen atoms to the complex chemistry of life, every step in this cosmic journey has shaped the universe we see today. And with that, let's move on to another fascinating piece of the puzzle: the role of cosmic dust during this enigmatic period. Now, let's shift our focus to another intriguing element of the Dark Ages: the role of cosmic dust. While it might seem like a minor detail, cosmic dust played a surprisingly significant part in shaping the early universe. Picture this: as the universe expanded and cooled, tiny particles of dust began to form, floating through the vast, dark expanse. These particles, though minuscule, had a big impact on the cosmic story unfolding around them. Cosmic dust is made up of tiny grains of solid matter, often consisting of elements like carbon, silicon, and oxygen. During the Dark Ages, these grains acted as seeds for chemical reactions, providing surfaces where atoms could meet and bond. This was especially important for the formation of molecules like molecular hydrogen, which we discussed earlier. Without cosmic dust, the process of molecule formation might have been far slower, delaying the birth of the first stars and galaxies. One of the key roles of cosmic dust was its ability to absorb and re-emit light. Even though the universe was dark during this era, the dust particles absorbed the faint radiation that existed, heating up slightly and then releasing that energy back into space. This process helped regulate the temperature of gas clouds, making it easier for them to collapse and form stars. In a way, cosmic dust acted like a cosmic thermostat, subtly influencing the conditions needed for star formation. Another fascinating aspect of cosmic dust is its role in shielding molecules from destructive radiation. In the early universe, intense ultraviolet light from the first stars and other sources could break apart molecules, preventing them from forming or surviving. But cosmic dust provided a protective barrier, absorbing this harmful radiation and allowing molecules to thrive in its shadow. This protection was crucial for the development of more complex chemistry, paving the way for the rich diversity of molecules we see today. Scientists believe that cosmic dust may have also played a part in the formation of the first solid structures in the universe. As dust grains collided and stuck together, they could have formed larger clumps, eventually leading to the creation of asteroids, comets, and even the seeds of planets. While this process would have taken millions of years, it highlights just how important these tiny particles were in shaping the cosmos. As we explore the role of cosmic dust, it's clear that even the smallest components of the universe can have a profound impact. From aiding molecule formation to regulating temperatures and shielding delicate chemistry, cosmic dust was a silent but essential player in the story of the Dark Ages. And with that, let's turn our attention to another fascinating piece of the puzzle: the impact of supermassive black holes during this mysterious era. Now, let's venture into one of the most mysterious and powerful forces in the universe: supermassive black holes. These cosmic giants, with masses millions or even billions of times greater than our Sun, are thought to have played a crucial role during the Dark Ages. But how did they form in such an early and seemingly empty universe, and what impact did they have on the cosmos as it evolved? The formation of supermassive black holes during the Dark Ages is still a topic of intense research and debate. One leading theory suggests that they grew from smaller seed black holes, which themselves could have formed from the collapse of massive stars or dense gas clouds. These seeds would have gradually accumulated more mass over time, either by consuming nearby gas and dust or by merging with other black holes. In the dense, chaotic environment of the early universe, this process could have accelerated, allowing some black holes to grow to supermassive proportions relatively quickly. Another intriguing possibility is that supermassive black holes formed directly from the collapse of massive gas clouds, bypassing the star stage entirely. In this scenario, vast clouds of gas, influenced by dark matter and cosmic filaments, could have collapsed under their own gravity, forming black holes with enormous masses right from the start. This would have been a rare but significant event, creating black holes that could dominate their surroundings and shape the evolution of galaxies. Once formed, supermassive black holes would have had a profound impact on their environment. Their immense gravitational pull would have drawn in surrounding gas and dust, creating swirling disks of material known as accretion disks. As this material spiraled inward, it would have heated up, emitting intense radiation that could ionize nearby gas. This process might have contributed to the reionization of the universe, helping to end the Dark Ages by lighting up the cosmos once again. Supermassive black holes also likely played a key role in the formation of the first galaxies. As they grew, their gravitational influence would have attracted and compressed gas clouds, triggering the collapse of these clouds into stars and star clusters. Over time, these clusters would have merged, forming the earliest galaxies. In this way, supermassive black holes may have acted as cosmic architects, shaping the large-scale structure of the universe. But the influence of supermassive black holes didn't stop there. Their powerful jets and outflows, driven by magnetic fields and the immense energy of their accretion disks, could have pushed gas and dust outward, regulating star formation in their host galaxies. These outflows might have prevented galaxies from growing too quickly, ensuring a more balanced and sustainable evolution of the cosmos. As we consider the impact of supermassive black holes, it's clear that these enigmatic objects were far more than just cosmic vacuum cleaners. They were dynamic, active participants in the story of the universe, shaping its structure, lighting its darkness, and influencing the birth of galaxies. And with that, let's turn our attention to another fascinating piece of the puzzle: the role of cosmic radiation during the Dark Ages. Now, let's shift our focus to another invisible yet powerful force that played a role during the Dark Ages: cosmic radiation. This radiation, a remnant of the Big Bang, permeated the early universe, influencing its evolution in ways that are still being unraveled by scientists today. But what exactly is cosmic radiation, and how did it shape this mysterious era? Cosmic radiation, often referred to as the afterglow of the Big Bang, consists of high-energy particles and electromagnetic waves that filled the universe shortly after its birth. During the Dark Ages, this radiation was one of the few sources of energy in an otherwise cold and dark cosmos. While it didn't emit visible light, it interacted with matter in subtle yet significant ways, leaving its mark on the universe's development. One of the key roles of cosmic radiation during the Dark Ages was its influence on the temperature of the universe. As the universe expanded and cooled, this radiation also lost energy, but it continued to interact with the sparse gas and dust that existed at the time. These interactions helped regulate the temperature of the early universe, preventing it from cooling too rapidly. This delicate balance was crucial for the formation of the first structures, as even slight changes in temperature could have altered the course of cosmic evolution. Another important aspect of cosmic radiation is its ability to ionize atoms. While the universe was mostly neutral during the Dark Ages, cosmic radiation could occasionally strip electrons from atoms, creating small pockets of ionized gas. These ionized regions, though rare, may have acted as seeds for future star formation. Over time, as more gas became ionized, these regions could have grown, eventually leading to the formation of the first stars and galaxies. Cosmic radiation also played a role in shaping the cosmic microwave background, or CMB, which we observe today. The CMB is essentially a snapshot of the universe as it was during the Dark Ages, and the patterns we see in it are a direct result of the interactions between cosmic radiation and matter. By studying these patterns, scientists can gain insights into the conditions of the early universe and the processes that led to the end of the Dark Ages. Interestingly, cosmic radiation may have also influenced the distribution of matter in the universe. As it traveled through space, it could have exerted pressure on gas clouds, subtly pushing them around and contributing to the formation of cosmic structures. This process, known as radiation pressure, might have played a small but significant role in shaping the large-scale structure of the universe we see today. As we explore the role of cosmic radiation, it becomes clear that this invisible force was far from passive. It was an active participant in the story of the Dark Ages, shaping the universe in ways that are still being discovered. And with that, let's turn our attention to another intriguing piece of the puzzle: the mystery of the first light and how it marked the end of the Dark Ages. Now, as we step into the next chapter of this cosmic story, we encounter a moment that forever changed the universe: the emergence of the first light. This wasn't just any light, it was the dawn of a new era, the signal that the Dark Ages were coming to an end. But what exactly was this first light, and how did it illuminate the cosmos after billions of years of darkness? The first light refers to the moment when the earliest stars and galaxies began to shine, breaking through the veil of neutral hydrogen that had cloaked the universe. These stars, known as population 3 stars, were unlike anything we see today. They were massive, hot, and incredibly bright, powered by the purest forms of hydrogen and helium left over from the Big Bang. Their formation marked a turning point as their intense ultraviolet radiation began to ionize the surrounding gas, carving out pockets of light in the darkness. This process, known as reionization, didn't happen overnight. It unfolded over hundreds of millions of years as more stars ignited and galaxies began to take shape. The first light didn't just illuminate the universe, it transformed it. By ionizing the neutral hydrogen, these early stars and galaxies made the universe transparent to light, allowing it to travel freely for the first time. This was the end of the cosmic fog that had defined the Dark Ages and the beginning of the universe as we know it today. But the first light wasn't just a cosmic switch being flipped. It was a complex, gradual process that involved countless stars and galaxies working together to reshape the universe. Each new star added to the growing glow, pushing back the darkness bit by bit. Over time, these individual points of light merged into a cosmic tapestry, creating the first large-scale structures in the universe. Interestingly, the first light also left behind clues that scientists are still deciphering today. The light from these early stars traveled across the universe, carrying with it information about the conditions of the early cosmos. By studying this ancient light, astronomers can piece together the story of how the first stars and galaxies formed and how they brought an end to the Dark Ages. It's like reading a cosmic diary written in the language of light. As we reflect on the mystery of the first light, it's impossible not to marvel at its significance. This wasn't just the end of an era, it was the beginning of everything we see around us today. The stars, the galaxies, even the light that fills our night sky, all trace their origins back to this pivotal moment. And with that, let's turn our gaze to another fascinating piece of the puzzle: the role of exotic particles and how they might have influenced the Dark Ages. Now, as we venture deeper into the mysteries of the Dark Ages, we turn our attention to a fascinating and speculative idea: the role of exotic particles. These elusive particles, often referred to as weakly interacting massive particles or WIMP, might have played a crucial role in shaping the universe during this enigmatic period. But what exactly are these particles, and how could they have influenced the cosmos when it was shrouded in darkness? Exotic particles like WIMP are hypothetical entities that scientists believe could make up a significant portion of dark matter. Unlike ordinary matter, these particles don't interact with light or other forms of electromagnetic radiation, making them invisible to traditional telescopes. Yet, their gravitational effects are thought to be immense, potentially influencing the formation of cosmic structures even during the Dark Ages. If WIMP or similar particles existed, they could have acted as the unseen scaffolding upon which the first galaxies and stars began to form. One intriguing possibility is that these particles might have provided the gravitational pull needed to gather clouds of hydrogen and helium, the raw materials for the first stars. Without the presence of dark matter, which is believed to be dominated by exotic particles, the universe might have remained a diffuse, featureless expanse for much longer. In this way, WIMP could have been the silent architects of the cosmos, guiding the formation of the first structures that eventually brought light to the universe. Another fascinating aspect of exotic particles is their potential to influence the temperature and density of the early universe. Some theories suggest that WIMP could have collided with ordinary matter, transferring energy and subtly altering the conditions that led to star formation. These interactions, though rare, might have been enough to create small variations in the density of the universe, seeding the regions where galaxies would later emerge. It's a delicate dance between the visible and the invisible, with exotic particles playing a hidden but vital role. While the existence of WIMP remains unconfirmed, their potential impact on the Dark Ages is a topic of intense research. Scientists are using advanced detectors and experiments to search for these elusive particles, hoping to uncover clues about their properties and their role in cosmic history. If discovered, WIMP could provide a missing piece of the puzzle, helping us understand how the universe transitioned from darkness to light. As we ponder the influence of exotic particles, it's clear that the Dark Ages were shaped by forces both seen and unseen. From the first light of stars to the invisible pull of dark matter, the cosmos is a tapestry woven from countless threads, each contributing to the grand story of the universe. And with that, let's shift our focus to another intriguing aspect of this cosmic mystery: the influence of cosmic voids and how they might have formed during the Dark Ages. Now, let's turn our gaze to one of the most intriguing features of the cosmos, cosmic voids. These vast, seemingly empty regions of space are not just gaps in the universe, they are key players in the story of the Dark Ages. Imagine the universe as a cosmic sponge with galaxies and clusters forming the dense, interconnected filaments, and the voids acting as the empty spaces in between. But how did these voids come to be, and what role did they play during the Dark Ages? During the early universe, tiny fluctuations in density, those same quantum ripples we discussed earlier, began to grow. Over time, regions with slightly higher density pulled in more matter through gravity, forming the seeds of galaxies and clusters. Meanwhile, the areas with lower density were left behind, gradually emptying out as matter flowed toward the denser regions. This process, driven by gravity, created the cosmic voids we observe today. But here's the twist: these voids weren't just passive bystanders. They actively shaped the universe during the Dark Ages. One of the most fascinating aspects of cosmic voids is their role in the distribution of matter. As matter flowed out of these regions, it left behind a near vacuum, a space where the density of matter is incredibly low. This lack of matter meant that voids were cooler and less energetic than the surrounding regions, creating a stark contrast in the early universe. These differences in temperature and density had a profound impact on the formation of structures. The voids acted like cosmic pressure points, influencing how galaxies and clusters formed around them. In a way, they were the negative space that defined the positive structures of the universe. But cosmic voids weren't just empty, they were filled with something else: dark energy. As the universe expanded, dark energy began to dominate, accelerating the growth of these voids. The interplay between dark energy and the gravitational pull of matter created a dynamic tension, shaping the large-scale structure of the cosmos. During the Dark Ages, this tension was at its peak, as the universe transitioned from a matter-dominated era to one ruled by dark energy. The voids, in this sense, were the battlegrounds where these two forces clashed, leaving their mark on the fabric of space. The significance of cosmic voids extends beyond their role in structure formation. They also serve as natural laboratories for testing our understanding of the universe. Because voids are so empty, they are less affected by the chaotic processes that occur in denser regions, making them ideal for studying the effects of dark energy and the expansion of the universe. By observing how light travels through these voids, scientists can gain insights into the properties of dark energy and the overall geometry of the cosmos. In this way, cosmic voids are not just relics of the Dark Ages, they are windows into the fundamental nature of the universe. As we reflect on the influence of cosmic voids, it's clear that these seemingly empty regions are anything but insignificant. They are the silent architects of the universe's large-scale structure, shaping the cosmos in ways we are only beginning to understand. And with that, let's move forward to explore another piece of the cosmic puzzle: the role of quantum gravity and how it might explain the mysteries of the Dark Ages. Now, let's venture into the realm of the incredibly small to uncover one of the most profound mysteries of the cosmos: quantum gravity. While gravity is the force that shapes the universe on the largest scales, quantum mechanics governs the behavior of particles at the tiniest levels. But what happens when these two worlds collide? This is where quantum gravity comes into play, and it might hold the key to understanding some of the most puzzling aspects of the Dark Ages. During the Dark Ages, the universe was a vastly different place. It was a time before stars and galaxies, when the cosmos was filled with a dense fog of neutral hydrogen. But even in this seemingly uniform environment, tiny fluctuations in density were at work, setting the stage for the structures we see today. These fluctuations are thought to have originated from quantum effects in the early universe, moments after the Big Bang. Quantum gravity seeks to explain how these microscopic ripples could have influenced the large-scale structure of the universe during the Dark Ages. One of the central ideas in quantum gravity is that space and time themselves are not smooth and continuous as we perceive them, but are instead made up of discrete, indivisible units. Imagine the fabric of the universe as a finely woven tapestry, with each thread representing a tiny quantum of space and time. During the Dark Ages, these quantum threads would have been constantly shifting and interacting, creating subtle variations in the density of matter. Over time, these variations grew, driven by gravity, eventually leading to the formation of the first stars and galaxies. But quantum gravity doesn't just explain the origins of cosmic structures, it also offers insights into the behavior of the universe during the Dark Ages. For instance, some theories suggest that quantum gravity could have influenced the rate at which the universe expanded. In the early universe, the interplay between gravity and quantum effects might have caused brief periods of accelerated expansion, known as inflation. These bursts of growth would have left their mark on the distribution of matter, shaping the cosmic voids and filaments we observe today. Another intriguing possibility is that quantum gravity could have played a role in the formation of primordial black holes. These hypothetical objects, thought to have formed in the early universe, could have been the result of quantum fluctuations collapsing under their own gravity. If they existed, primordial black holes might have acted as seeds for the formation of galaxies, providing the gravitational pull needed to gather matter into dense clumps. During the Dark Ages, these black holes could have influenced the distribution of matter, leaving behind a cosmic fingerprint that we are only now beginning to detect. As we explore the role of quantum gravity, it's important to remember that this is still a developing field of study. While we have some tantalizing clues, much remains to be discovered. The challenge lies in reconciling the vast scales of gravity with the minuscule world of quantum mechanics. Yet, the potential rewards are immense. By understanding quantum gravity, we could unlock the secrets of the Dark Ages and gain a deeper understanding of the universe's origins. With this in mind, let's turn our attention to another fascinating piece of the cosmic puzzle: the mystery of the first quasars and their role in bringing an end to the Dark Ages. Now, as we shift our gaze to the dawn of cosmic illumination, we encounter one of the most enigmatic and powerful objects in the universe, the first quasars. These brilliant beacons of light, born from the chaos of the early cosmos, played a pivotal role in bringing an end to the Dark Ages. But what exactly are quasars, and how did they emerge from the shadows of the universe's earliest days? Quasars, short for quasi-stellar radio sources, are among the most luminous objects in the cosmos. They are powered by supermassive black holes at the centers of young galaxies, devouring vast amounts of matter and releasing staggering amounts of energy in the process. But the story of the first quasars begins long before their light pierced the darkness. It starts with the collapse of the first massive structures in the universe, which formed from the seeds planted by quantum fluctuations during the Dark Ages. As matter began to clump together under the pull of gravity, the first proto-galaxies took shape. Within these dense clouds of gas and dust, the first supermassive black holes began to form. These black holes, growing rapidly as they consumed surrounding matter, became the engines that powered quasars. The intense gravitational forces around these black holes heated the infalling gas to incredible temperatures, causing it to glow brightly across the electromagnetic spectrum. This light, streaming out into the universe, marked the beginning of the end for the Dark Ages. The radiation from quasars was so powerful that it began to ionize the neutral hydrogen that had dominated the universe for hundreds of millions of years. This process, known as reionization, gradually cleared the cosmic fog, allowing light to travel freely through space once again. Quasars, along with the first stars and galaxies, were the cosmic pioneers that illuminated the universe, transforming it from a dark, featureless expanse into the vibrant, structured cosmos we see today. But the role of quasars didn't end with reionization. their intense radiation also influenced the formation of galaxies and the distribution of matter in the universe. The energy they released could heat surrounding gas, preventing it from collapsing into new stars and shaping the growth of galaxies. In this way, quasars not only ended the Dark Ages but also helped sculpt the large-scale structure of the universe. The mystery of the first quasars is far from solved, however. How did supermassive black holes grow so quickly in the early universe? What triggered the formation of the first quasars, and how did they influence the evolution of galaxies? These questions remain at the forefront of astrophysical research, with astronomers using cutting-edge telescopes to peer back in time and uncover the secrets of these ancient cosmic powerhouses. As we continue our journey through the theories of the Dark Ages, let's turn our attention to another fascinating piece of the cosmic puzzle: the role of cosmic filaments in shaping the universe during this mysterious era. Shifting our focus to the intricate web that holds the universe together, we now explore the role of cosmic filaments during the Dark Ages, often referred to as the skeleton of the cosmos. These vast, thread-like structures of gas and dark matter stretch across the universe, connecting galaxies and clusters in a sprawling network. But how did these filaments come to be, and what role did they play in the era before the first stars and galaxies lit up the sky? The story of cosmic filaments begins with the seeds of structure planted by quantum fluctuations in the early universe. These tiny ripples in the fabric of space-time, amplified by cosmic inflation, created regions of slightly higher density. Over time, gravity began to pull matter toward these denser areas, setting the stage for the formation of the universe's large-scale structure. During the Dark Ages, as the universe expanded and cooled, these regions of higher density started to collapse, forming long, thin strands of gas and dark matter, the first cosmic filaments. These filaments served as the highways along which matter flowed, channeling gas and dark matter into the nodes where galaxies and clusters would eventually form. Picture the universe as a vast, interconnected network, with filaments acting as the bridges that link everything together. Without these structures, the universe would lack the intricate organization we see today. They are the backbone of the cosmic web, shaping the distribution of matter on the largest scales. But cosmic filaments didn't just passively exist during the Dark Ages, they played an active role in the universe's evolution. As matter flowed along these filaments, it accumulated at their intersections, creating the dense environments where the first galaxies and supermassive black holes could form. This process was crucial for ending the Dark Ages, as the accumulation of matter in these regions led to the birth of the first stars and quasars, whose light began to reionize the universe. Interestingly, cosmic filaments also influenced the way galaxies evolved. The flow of gas along these structures provided a steady supply of fuel for star formation, while the gravitational interactions between filaments and galaxies shaped their growth and movement. Even today, cosmic filaments continue to play a vital role in the universe, guiding the motion of galaxies and influencing the distribution of matter on a grand scale. The study of cosmic filaments is still in its early stages, with astronomers using advanced simulations and observations to unravel their mysteries. How did these structures form so early in the universe's history? What role did they play in the transition from the Dark Ages to the era of reionization? These questions remain at the cutting edge of astrophysical research, offering a glimpse into the forces that shape the cosmos. As we continue to piece together the story of the Dark Ages, let's turn our attention to another fascinating aspect of this cosmic era: the influence of cosmic collisions on the formation of the universe's first structures. Now, let's dive into the dramatic and dynamic world of cosmic collisions and their profound influence during the Dark Ages. Imagine the early universe as a chaotic, bustling arena, where the first structures, clumps of gas, dark matter, and primordial galaxies, were constantly interacting, merging, and colliding. These cosmic collisions weren't just random events. They were pivotal moments that shaped the universe's evolution and played a key role in bringing an end to the Dark Ages. During this era, the universe was still relatively young, and matter was distributed unevenly, with denser regions beginning to form the first structures. As gravity pulled these regions closer together, collisions became inevitable. When two clumps of gas or dark matter collided, the impact generated shock waves, heating the surrounding material and triggering bursts of activity. These collisions were like cosmic sparks, igniting the processes that would eventually lead to the formation of stars and galaxies. One of the most significant outcomes of these collisions was the creation of dense, turbulent environments. When gas clouds collided, they compressed, increasing the density of the material and creating the perfect conditions for star formation. This was a crucial step in ending the Dark Ages, as the first stars began to light up the universe, breaking through the darkness and initiating the era of reionization. Without these collisions, the universe might have remained in its dark, neutral state for much longer. But the influence of cosmic collisions didn't stop there. These events also played a role in shaping the distribution of matter on larger scales. When smaller structures merged, they formed larger, more complex systems, such as the first galaxies and galaxy clusters. These mergers not only increased the mass of these structures, but also influenced their shape and movement. For example, when two galaxies collided, their gravitational interactions could stretch and twist their shapes, creating the intricate spiral and elliptical galaxies we observe today. Interestingly, cosmic collisions also contributed to the formation of supermassive black holes. When gas-rich galaxies collided, the influx of material into their centers could trigger the rapid growth of these black holes, which would later become the powerhouses of quasars. These luminous objects played a critical role in reionizing the universe, as their intense radiation helped strip electrons from hydrogen atoms, bringing an end to the Dark Ages. The study of cosmic collisions during the Dark Ages is still a vibrant area of research. Astronomers use sophisticated simulations to recreate these events, helping us understand how they influenced the universe's evolution. Questions remain about the frequency and impact of these collisions, as well as their role in shaping the cosmic web we see today. As we reflect on the role of cosmic collisions, let's turn our attention to another fascinating piece of the puzzle: the role of primordial nucleosynthesis in shaping the early universe. How did the creation of the first elements set the stage for the Dark Ages and beyond? Stay with us as we explore this next chapter in the story of the cosmos. Now let's journey back to the very beginning, to a time when the universe was just a hot, dense soup of particles and energy. This is where the story of primordial nucleosynthesis begins, a process that not only shaped the early universe but also set the stage for the Dark Ages that followed. Primordial nucleosynthesis refers to the creation of the first light elements, hydrogen, helium, and trace amounts of lithium in the minutes following the Big Bang. As the universe expanded and cooled, conditions became just right for protons and neutrons to combine, forming these simple elements. This process was incredibly efficient, producing the building blocks of all matter we see today. In fact, nearly all the hydrogen and helium in the universe today can be traced back to this brief but critical period. But how does this connect to the Dark Ages? Well, the elements created during primordial nucleosynthesis became the raw materials for everything that came after. Hydrogen, in particular, played a starring role. During the Dark Ages, the universe was filled with neutral hydrogen gas, which absorbed light and kept the cosmos shrouded in darkness. This hydrogen was a direct product of nucleosynthesis, and its abundance dictated the conditions of the early universe. The distribution of these light elements also influenced the formation of the first structures. Regions with slightly more hydrogen and helium became denser over time, pulled together by gravity to form the first clumps of matter. These clumps would eventually grow into stars, galaxies, and the cosmic web we see today. Without the elements forged in those first few minutes, the universe as we know it simply wouldn't exist. Interestingly, the ratio of hydrogen to helium created during nucleosynthesis also had long-term effects. Helium, being heavier, influenced how gas cooled and collapsed, affecting the formation of the first stars. These stars, in turn, would go on to reionize the universe, ending the Dark Ages and lighting up the cosmos once more. Primordial nucleosynthesis didn't just set the stage for the Dark Ages, it laid the foundation for the entire universe. By understanding this process, we gain insight into the origins of matter itself and how the cosmos evolved from a hot, dense state to the complex, luminous universe we observe today. As we reflect on the significance of these first elements, let's shift our focus to another cosmic mystery: the role of the first supernova in shaping the universe. How did these explosive events contribute to the end of the Dark Ages? Stay with us as we explore this next chapter in the story of the cosmos. Now, let's turn our attention to one of the most dramatic events in the early universe, the first supernova. These colossal explosions didn't just light up the cosmos, they played a pivotal role in bringing an end to the Dark Ages. But how exactly did these fiery giants shape the universe as we know it? Supernovae are the explosive deaths of massive stars, and the first ones occurred when the earliest stars, known as population 3 stars, reached the end of their lifespans. These stars were unlike anything we see today: immense, hot, and composed almost entirely of hydrogen and helium, the elements forged during primordial nucleosynthesis. When these stars exhausted their fuel, they collapsed under their own gravity and exploded in spectacular fashion, scattering their contents across the cosmos. The aftermath of these explosions was transformative. Supernova released enormous amounts of energy, heating the surrounding gas and ionizing the neutral hydrogen that had dominated the universe during the Dark Ages. This process, known as reionization, began to clear the cosmic fog, allowing light to travel freely once more. It was as if the universe had flipped a switch, transitioning from darkness to light. But the impact of the first supernova didn't stop there. These explosions also seeded the universe with heavier elements such as carbon, oxygen, and iron, which had been forged in the hearts of the dying stars. These elements, scattered into space, became the building blocks for future generations of stars, planets, and even life itself. Without the first supernova, the universe would have remained a much simpler place, devoid of the complexity we see today. Interestingly, the shock waves from these explosions also played a role in shaping the cosmic landscape. They triggered the collapse of nearby gas clouds, compressing them and accelerating the formation of new stars and galaxies. In this way, the first supernova didn't just end the Dark Ages, they set the stage for the universe's ongoing evolution. As we piece together the story of these ancient explosions, we gain a deeper understanding of how the universe transitioned from darkness to light. The first supernova were not just cosmic fireworks, they were the catalysts that reshaped the cosmos, paving the way for the vibrant universe we inhabit today. With this explosive chapter in mind, let's now explore another fascinating aspect of the Dark Ages: the role of cosmic feedback. How did the radiation and energy from early stars and supernova influence the universe's evolution? Stay tuned as we uncover the next piece of this cosmic puzzle. Now, shifting our focus to another critical piece of the cosmic puzzle, let's dive into the role of cosmic feedback during the Dark Ages. This concept revolves around how the energy and radiation emitted by early stars and supernova influenced the universe's evolution, shaping the environment in profound ways. Cosmic feedback refers to the processes by which the first stars and their explosive deaths released energy and radiation into the surrounding space, altering the conditions of the early universe. Imagine these stars as cosmic architects, not only illuminating the darkness but also reshaping the very fabric of the cosmos. Their radiation didn't just travel through space, it interacted with the gas and matter around them, heating it up and driving changes that would have lasting effects. One of the most significant impacts of this feedback was its role in reionization. As the first stars burned brightly, their ultraviolet light began to ionize the neutral hydrogen that had dominated the universe during the Dark Ages. This process didn't happen all at once. It was a gradual transformation, like a ripple spreading across a pond. Over time, these ripples of ionizing radiation cleared the cosmic fog, allowing light to travel freely and marking the end of the Dark Ages. But cosmic feedback didn't stop at reionization. The energy from early stars and supernovae also influenced the formation of new structures in the universe. For instance, the intense radiation from these stars could push gas clouds apart, preventing them from collapsing to form new stars in some regions. In other areas, the shock waves from supernova compressed gas clouds, triggering the birth of new stars and galaxies. This delicate balance between destruction and creation was a key driver of the universe's evolution during this period. Another fascinating aspect of cosmic feedback is how it contributed to the chemical enrichment of the universe. The first stars and supernova didn't just release energy, they also scattered heavier elements like carbon, oxygen, and iron into space. These elements, forged in the hearts of stars and dispersed by their explosive deaths, became the raw materials for future generations of stars, planets, and even life. Without this feedback, the universe might have remained a much simpler place, devoid of the complexity we see today. As we explore the role of cosmic feedback, it's clear that these mechanisms were more than just side effects of stellar activity. They were fundamental forces that shaped the universe during the Dark Ages and beyond. By understanding how energy and radiation from early stars influenced the cosmos, we gain a deeper appreciation for the intricate processes that transform the universe from darkness to light. With this in mind, let's now turn our attention to the future of Dark Ages research. What new discoveries await us as we continue to probe the mysteries of this enigmatic era? Stay tuned as we explore the cutting-edge tools and missions that are helping us uncover the secrets of the universe's earliest days. As we look ahead, the future of Dark Ages research is brimming with promise, thanks to groundbreaking tools and missions designed to peel back the layers of this mysterious cosmic era. One of the most exciting developments is the upcoming James Webb Space Telescope, which is set to revolutionize our understanding of the early universe. With its unparalleled sensitivity to infrared light, this telescope will allow us to peer further back in time than ever before, capturing the faint glow of the first stars and galaxies that emerged from the darkness. But the James Webb Space Telescope is just the beginning. Another ambitious project on the horizon is the Square Kilometre Array, or SCAR, a massive radio telescope network that will map the universe in unprecedented detail. By detecting the faint signals of neutral hydrogen from the Dark Ages, the SKA aims to create a three-dimensional map of the early cosmos, revealing how structures formed and evolved over billions of years. This could provide crucial insights into the processes that shaped the universe during its most enigmatic phase. In addition to these telescopes, missions like the Nancy Grace Roman Space Telescope are set to explore the cosmic dawn in new ways. By studying the distribution of galaxies and dark matter, this telescope will help us understand how the first stars and galaxies influenced the universe's large-scale structure. Together, these missions represent a new era of discovery, offering the potential to answer questions that have puzzled scientists for decades. Beyond these technological marvels, theoretical advancements are also pushing the boundaries of our knowledge. Researchers are developing sophisticated models to simulate the conditions of the early universe, incorporating factors like dark matter, dark energy, and cosmic feedback. These simulations, combined with observational data, are helping us piece together a more complete picture of the Dark Ages and the forces that shaped the cosmos. As we continue to explore this fascinating period, one thing is clear: the Dark Ages are no longer as dark as they once seemed. With each new discovery, we're shedding light on the universe's earliest days, uncovering the secrets of how it transformed from a sea of darkness into the vibrant, complex cosmos we see today. The journey is far from over, and the next chapter of Dark Ages research promises to be as thrilling as the discoveries that have come before. And with that, we've reached the end of our exploration of the 30 theories about the universe's dark ages. From the first stars to the role of dark matter, each theory offers a unique perspective on this mysterious era. If you've enjoyed this cosmic journey, don't forget to like, subscribe, and hit the notification bell for more deep dives into the mysteries of the universe. Until next time, keep looking up, there's always more to discover. As we wrap up this cosmic journey through the 30 theories about the universe's dark ages, it's clear that this mysterious era holds the key to understanding how our universe evolved from a dark, featureless void into the vibrant, star-filled cosmos we see today. From the clues hidden in the cosmic microwave background to the role of dark matter and the birth of the first stars, each theory offers a unique piece of the puzzle, helping us piece together the story of the universe's earliest days. The importance of studying the Dark Ages cannot be overstated. This period, though shrouded in mystery, laid the foundation for everything that followed: galaxies, stars, planets, and even life itself. By unraveling its secrets, we gain not only a deeper understanding of our cosmic origins, but also insights into the fundamental forces that shape the universe. As we've seen, the tools and technologies at our disposal are more powerful than ever, from the James Webb Space Telescope to the Square Kilometre Array. These advancements are opening new windows into the past, allowing us to explore the universe's infancy with unprecedented clarity. And with each discovery, we're reminded that the cosmos is full of wonders waiting to be uncovered. If you've enjoyed this deep dive into the mysteries of the Dark Ages, don't forget to share your thoughts in the comments below. What theory fascinated you the most? Which cosmic mystery do you think holds the most promise for future discoveries? Let's keep the conversation going. And if you're eager for more explorations into the universe's greatest enigmas, hit that subscribe button and ring the notification bell so you never miss out on our next cosmic adventure. Thank you for joining us on this journey through the Dark Ages. Remember, the universe is vast and its stories are endless. Keep looking up, there's always more to discover.